Hello, welcome to another video lecture of OpenStax Astronomy. We'll be looking at Chapter 11, the giant planets. And so here's a quick preview of the Jovian planets, Jupiter, Saturn, Uranus, and Neptune. And this is not to scale as far as distance, but it is to scale as far as size. And we could see that we have Earth there just as a comparison. You could fit roughly about 1,300 Earths inside of Jupiter just to kind of get a sense of scale. Here's some statistics here on distance, periods, and then rotational hours. So looking at Jupiter, rotates in about 10 hours. Saturn about 11 hours. And so these are a lot larger than the terrestrial planets. So they are rotating a lot faster. And we typically talk about that rotation at the equator. The Jovian planets are not solid. They're gas hydrogen compounds. And so they will rotate at different speeds depending on what latitude you're at. But these are estimates roughly at about on the equator. So some exploration with the Jovian planets. We've had quite a few space probes go out, take images, so we know quite a bit about them. And we'll look at some of these images in high resolution. Just amazing the clarity that we're able to get. Here's one of those images. This is Cassini, and when it passed Saturn, it kind of turned around and took a selfie. So there at the bottom in the arrow is Earth. So kind of turned around, took a nice selfie shot there back at Earth, which is about 1.4 billion kilometers away. Extremely remarkable. So the giant planets, the Jovian cores are very similar to a mass of about 10 Earths. But they do differ in the amount of hydrogen and helium gas that's accumulated. So why do these differ slightly? And so let's look first at the interior here of how they differ. So there are a lot of hydrogen compounds. So this molecular hydrogen varies in liquid and gas hydrogen. And so we could see that Jupiter and Saturn has a lot of metallic hydrogen. Uranus and Neptune, not as much. And so the internal structures of Jupiter and Saturn are very closely related, and then Uranus and Neptune as well. Uranus and Neptune, again, have some parts compound of carbon, nitrogen, and oxygen as well. Let's take a closer look here at Jupiter. And so the Jovian planets don't have a solid surface. So if you were to stand or descend into it, you would just kind of sink further and further in. So where the atmosphere ends and the actual surface kind of just mashes together. So in Jupiter, we have these cloud tops. You have gas hydrogen, liquid hydrogen, and then a metallic hydrogen. And then there is a core of rock metals, but not as much compared to all of that hydrogen compounds that we have. So again, looking at the interiors here of the different hydrogen compounds, we see that there's lower pressures in Uranus and Neptune. So without that high pressure, you're not able to get that metallic hydrogen. So you need a lot of that pressure pushing inwards on it. And that's the main difference. Jupiter and Saturn are extremely larger, so you'll be able to have that pressure, making that different hydrogen compound. Some difference in densities here. So interesting here is we see that Saturn is actually less than 1. Water is rated at 1, so if there was theoretically a large enough body of water, Saturn would technically float on that. And so we'll talk a little bit of why that is, why Saturn is has slightly lower density there. And this has to do with the size. So once the sun started fusing and the solar winds started, it started pushing a lot of the leftover debris towards the outer part of the solar system. Jupiter, being larger, captured majority of that, and being closer as well, captured the more abundance of that hydrogen. And so as it gets more and more, gravity is able to actually compact it a bit more, so it actually gets compressed. So it becomes denser and denser. So just fitting in, the more you have on it, the more of that gas, underlying gas layer, and it's going to be able to get compressed further and further. So the bigger you get, the more you're able to compress. And so that's the main difference between Jupiter and Saturn, that it was allowed to have that adding a lot of mass to compress those underlying gas layers. Jupiter also has a strong magnetic field. And we could see this relationship with these ionized or charged particles. So similar to that of Earth's magnetic field, Jupiter behaves in the same fashion, where particles coming out from the solar winds get ionized, charged. They travel along that magnetic field and they enter in at the poles. And so they create some remarkable auroras on Jupiter on both of the poles. Here's an image in a radio waves here, and we could see the magnetic sphere there. So extremely large, getting carried out, and we could see activity on both the North and South Pole. So let's discuss a little bit about the atmosphere of the Jovian planets. And so here we see an image of Jupiter's cloud line. And so when we're looking down on Jupiter, we don't really see the surface there. There's this thick concentration of cloud lines that blends in with the atmosphere. Here is a breakdown of the atmosphere for the 4 Jovian planets. Slight variation in the composition here. And the main thing to note here is with this yellow line indicated there is that it actually shows the change with temperature versus altitude. So the temperature is going to be one of the key components that creates the differences between the Jovian planets within the atmosphere, and then also going down towards into the core. Jupiter's atmosphere has some hydrogen compounds. We could see the different coloration here. So freezing points of different hydrogen compounds, and then creating the different colorations there. So kind of that more reddish, you'll see a grayish color, and then a more yellowish as well there. And so this has to do with different elevations, which in turn has to do with the different temperatures. So cold temperatures could condense water, giving that grayish color, versus if they start condensing ammonia, would be more of that reddish color. So Jupiter and Saturn as well have that kind of brownish red color of sulfide, and which reflects the kind of red-brown color. So high concentration of ammonia in those highest cloud layers, and that reflects more of that whitish color there. So as we look at this image, the different coloration, again, is going to be different elevations of cloud lines due to the composition. Here's an image of Saturn, and we could see similar colorations there. And again, the different coloration there indicating different altitudes with those cloud lines, but very similar to that of Jupiter's composition. Uranus and Neptune's atmosphere is slightly different. It has more methane gas, which absorbs that reddish brown color and transmits blue light. So when we look at Uranus and Neptune, they appear more of a bluish color. Again, that methane and ammonia that gets reflected out. Here's an actual image of the atmosphere on Neptune. And we could see that cloud line towards the center of that image there. And so those white clouds contain methane ice crystals, and they are slightly higher than the main cloud line. So how is the weather on the Jovian planets? And when we talk about weather, we're talking about on the surface. So what type of activity is happening on the surface there and even into the atmosphere. And what we see is that there are very, very strong winds. So here on Earth, if we have hurricanes typically form over the water, they get very strong. But as they move their way into land, land is a lot more solid surface, so those storms lose their momentum. The Jovian planets don't have any solid surface, and so when we have these storms, there really isn't material to slow them down. And so they're able to pick up and have strong winds, strong storms, and they could last for a very, very long time. And we see this across the 4 Jovian planets. The winds on the giant planets, again, vary with their rotation. And since they're not solid, rotations along the equator and towards the poles are going to be different. But here in this chart, we could kind of see the relationship of those winds with the latitude. This is Jupiter's Great Red Spot. It's a storm it fluctuates a little bit in size, but is typically about 2 to 3 Earths wide. So imagine that, a storm that's as big, larger than the Earth itself. And we have records that track this to about 300 years that this storm has been going on. Here's another image of the Great Red Spot, and again, fluctuating slightly in size there. And then you could see down below it even another storm that tends to form there. And so this storm, the Great Red Spot, is still going and has been going for a few centuries. Here's some more images of Jupiter looking at some storms. And we see in that first image 3 other oval storms there that tend to move closer over a period of several months there. So lots of activity, lots of storms happening throughout the surface of Jupiter. Saturn also has some weather, and its axis tilt is just about 27 degrees. So if you recall, Earth has that axis tilt of 23.5 degrees. and that's what creates the seasons. So Saturn has these high winds, also is going to have seasons because of that tilt, but they're not going to be as extreme year round. Here we could see the cloud structure of Saturn, and we could see bands and zones of some of the storms here in the atmosphere. And again, coloration indicating different heights of those cloud lines there. On the pole of Saturn, on the North Pole, there's a huge storm there, these jet streams here, of this hexagon kind of pattern shape there on that north. And the winds here are extremely violent, measured at about 1,800 kilometers per hour. So very, very large storm that takes up kind of the whole part of that northern pole on Saturn. Uranus has slightly larger axis tilt here, almost 90 degrees there. So this image here taken, and that first one you could see a few of the moons orbiting around, and then the rings also of Uranus there. But that large axis tilt is going to create more extreme seasons throughout the year. And so here, these strange seasons on Uranus here, where we see the amount of sunlight that we actually get. So for Uranus to make one orbit around takes roughly about 84 years. And so we'll see the amount of sun that we get right on that South Pole lasts for about 42 years, and then it dips down. Then it goes onto the North Pole. So it's we have one side facing the sun and then one side facing away. So decades of kind of getting that sunlight of that summer, and then you'll have decades of not of that winter region as well. Here is an image of Neptune, and we could see in the center there the dark spot here, which again is another large storm similar to the red great spot on Jupiter. This was taken back in the late 80s. This storm no longer exists. It has dissolved now, but still very, very, or Neptune very capable of having large storms within itself.